Hello and welcome to Gaffy's Grind. If this is your first time on the channel, you're very welcome. If you're one of my students or if you've been here before, welcome back. This is the first video in a series I'm about to do on back to the basics for titration calculations. So what I'm going to do is I'm going to try and keep all these videos in a playlist, titration calculation exam questions. And the idea here is some students, they get into the titrations, and I found it with my own students, they get into the titrations, we get 4 or 5 titrations through, and I'm kind of expecting people to be able to start getting the ideas of the calculations. And I'm finding that some of the students still, uh, whatever, maybe we just haven't spent enough time on it. They just don't have a full grasp on it. So the idea of this channel, and again, there's nothing wrong with that. A lot of this just comes from maybe not having enough practice, or I know in my case this year, me and my students, while we were doing these titrations, like these calculations, the summer came in the middle, and then after the summer we were doing the titrations, and maybe it's just that the calculations aren't fresh in their minds again. But the idea here is to go back to the basics. So my thinking here is we go back to the ordinary level questions and work our way through those because they're a bit easier and build up the confidence and build up the understanding of the relationships between the reacting chemicals, how to convert moles to moles per liter to moles and so on, and just build up students' confidence and your confidence this way through doing the ordinary level questions. As well as that, some of you may end up doing the ordinary level later on, or some of you may be here to learn how to do the ordinary level calculations. And again, this is a good place for you to learn that. So we're going to start by working our way through the ordinary level titration questions. There's one every year, and again, the idea is to work our way through them and build up to the higher level. Obviously, we need to get to the higher level ones at the end. Just a little background on the ordinary level. There's only one titration on the ordinary level paper, so it's always the same reaction. It's titration 1 from the higher level. It's a reaction between hydrochloric acid and sodium carbonate. You will have to know how to make up a standard solution of sodium carbonate using this guy here, this type of flask, which we might be asked about later on. You will need to know how to do that. You will need to know your procedures for using a pipette, using a burette, and so on. You will need to know what indicator you use, and you will need the basic titration calculations. So you can't get away from that, okay? You do need to know how to find out how to go between moles per liter to moles and so on. So you do need the basics, but typically the questions are easier and the information you need to use is usually more obvious. Okay, so if you've been here before, you know how this works. If you haven't been here before, typically how this works is I will talk through the question and I will regularly ask you to pause the video and do parts of the question. It's really, 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 really important that as soon as you can, that you are pausing the video and working ahead of me and only really playing to see how it's done and to make sure that you've done it right. Okay. If you are 7, 8 videos in and you're still just waiting for me to do it and copying what I do, then you're just relying too much on me as a crutch, and you're never going to be able to walk by yourself if you don't get rid of the crutch as soon as possible. Okay. All right, so let's jump into this question. This is the 2022, so just the summer gone, the 2022 ordinary level titration question was question 2. All right, so let's begin. If you've got, the best thing to do is get yourself a set of exam papers and work through these with me so you have a piece of paper actually underlined. All right, so let's work our way through. It said a student prepared a 0.05 molar solution of sodium carbonate. All right, good. So straight away we have a concentration. Okay, so molar means moles per liter. And we have the moles per liter of sodium carbonate by dissolving a known mass of anhydrous sodium carbonate, which is Na2CO3, in deionized water in a beaker and transferring the solution to a 250 centimeter cube volumetric flask. 200 centimeter cube volumetric flask, that's this guy over here. So if you'd forgotten the name of that, it told you it's a volumetric flask. Then the solution in the flask was made up to the mark by adding more deionized water. Okay, some information there. We may need to come back to that later. We may not, but definitely this is going to be important, I think. All right, so again, you're highlighting, you're annotating. You should be doing the same thing I'm doing. All right, so question 2, part A. It says, what term is used to describe a solution whose concentration is accurately known? So this is a standard definition that you guys are supposed to learn off, and hopefully you guys know the answer to this. So question 2, part A, what I'm going to get you to do is pause the video and write that down now. Okay, so a solution whose concentration is known Okay, we call this, again, you should only be playing the video if you've tried to do this yourself and written down the answer. What is a solution whose concentration is known called? Okay, so again, correct this if you got it right. It's called a standard solution. So standard solution is a solution whose concentration is accurately known. That's a pretty straightforward definition from this, and you can be sure it's going to be asked pretty regularly from this topic. All right, let's move on. That was what, 5 marks. All right, so again, probably a good idea to tick it if you got it right, and if you got it right, give yourself the 5 marks. Good. All right, let's move on. Describe how all the sodium carbonate solution in the beaker was transferred to the volumetric flask and then made up accurately to 250 centimeters cubed of solution with the same concentration throughout. Basically, what it's asking you is describe how you, it's told us we dissolved the solution, dissolved the powder in a beaker. How do we then add it to this flask and make it up to the mark? Okay, so B, the process for preparing that standard solution. All right, so it's worth 12 marks. So again, this is usually going to be 4 times 3. So we need 4 scoring points here. So let's pause the video and talk our way through how would we take our beaker of dissolved powder and add it to this flask and top it up to the mark. But all the accurate steps, be as detailed as you can. Pause the video and do this now. Okay, so you should only be playing if you've tried to do this. We're talking about how to make a standard solution. How to make a standard solution. So we already have the solution in the beaker. What we want to do now, first of all, is we need to put it in the volumetric. How do we add it to the volumetric with that narrow little neck? Okay, if you weren't talking about how do you add it without spilling, you should pause the video and add a bullet point for that now. Okay, so first of all, I would use a funnel. Use a funnel. Okay, and what are we doing with the funnel? To pour the contents of the beaker into the volumetric flask. Okay, what do we do then? Again, I've got you started. If you weren't able to keep this going on your own, now's the time to pause the video and try and get a few of these points yourself. Okay, so a good idea then always after you've poured it in is to rinse the beaker. Rinse the beaker, and we usually rinse it with deionized water. Deionized water. And add to the flask. To the flask. What do we do then? Okay, we're going to use a wash bottle. That's what my students do. They use a wash bottle to top up the flask. Okay, next point. If you didn't talk about how do you know when to stop filling? Okay, when do we stop? Until the bottom of the meniscus, and the meniscus is the curve like this. Here's the neck of the flask, and the meniscus is the curve of the liquid, and we want that to stop on the graduation mark. So until the bottom of the meniscus is on the graduation mark, and we've got loads of stuff here. We're definitely going to get all the marks. We've already got 4 scoring points, but keep finishing it anyway. Okay, and where do we read it from? Okay, so again, you should only be playing if you have written an answer for this. We should read it at eye level. We don't want to read it from up here. Okay, because that can lead us to make errors. If we read it from up here like that, this is wrong. We want to read it from eye level. Reading at eye level. And then how do we make sure that it's the same concentration all around the flask? Again, if you didn't talk about this, pause the video and do that now. Stopper and invert. Invert means turn upside down. So your teacher probably told you how to do this, invert it. And we want to do it several times. Some people say at least 20, but several is okay, several times. Okay, so that would definitely get you the marks if you had that level of detail. basically any of these bullet points here is scoring points. So we had more than enough. We can only get 4 times 3. That's the max available here. So we should have got the full 12 there. Well done. On to the next bit. Okay, so let's look at part C. It says the mass of 1 mole of sodium carbonate is 106 grams. Now, for you doing higher level, most of you will know that this amount here is called the molar mass, or the MR. So the molar mass of Na2CO3 is 106 grams. That's something you'll notice if you're a higher level student. You'll notice they don't tell you things like this at higher level. Oh, okay, so they give you information that you don't get at higher level. Makes it a little bit easier. What would the mass be of 0.05 moles of sodium carbonate? So if this is for this is the molar mass for 1 mole, what would the mass of sodium of 0.05 moles be? Okay, so we're going to do that out at the side here. C part 1. Okay, so I'm going to get you to figure that out. Okay, so hopefully you've had a go at that. The correct answer here is 5.3 grams. Now, I'm going to show you how to do it in a second, but if you didn't get 5.3 grams, have another go now and see can you make it work out to 5.3 grams. All right, so how would I do it here? Okay, well, the first thing I would say is I would say that I know it's 106 grams of what of the substance Na2CO3 per 1 mole. Okay, per 1 mole. So that's how many grams per mole we have. But I'm not talking about 1 mole. I want to convert this to a number of grams because it asks me how many grams are in 0.05 moles. So I want my answer over here to be in grams of Na2CO3. And my students will know what I'm talking about here. We need to set up a sum here which cancels out moles. Moles here is in the denominator, which means I want to make moles be in the numerator of this thing that I'm multiplying it by so that they cancel. And from the question, I know that it was how many are in 0.05 moles. So if I times that by 0.05 moles, then I will get an answer in grams. Okay, now you may have a different way of doing this, and that's okay, so long as you consistently get the right answer. But this, in my opinion, is the best way because by canceling out the units, you know you've done it right because your only unit that you've got left here is grams. Okay, so when we do this, you should get 5.3 grams of sodium carbonate. Well done if you got that right. That was only worth 3 marks. Okay, let's see what it said then. Calculate the mass of Na2CO3 required to prepare 250 centimeters cubed of a sodium carbonate solution of exactly 0.05 molar. Okay, so C part 2. C part 2. And I'm going to scroll back over so you can see the important pieces of text in case you don't have exam papers. And you have to calculate the mass required to prepare that solution. Okay, so some of you should know how to do this. Okay, and I'm going to give you the opportunity to pause the video with no help and to do this now. Okay, so pause the video and have a go at this now. Okay, so if you haven't been able to do this, or if you've done it and you're not sure if you have it right, here's your first hint. I'm going to give you what the answer should be. And again, this isn't just so you can write the answer and move on because that's not teaching you anything. But this is for you to see if you have it right, so you can be confident and you can know that you don't need to try it again. So you should be getting 1.325 grams is how much would be required to make that solution. Okay, so if you got that correct, well done. You can skip the next little bit and move on. But if you didn't get that right, then we need to figure out how to do this. We need to plan what we want to do. Okay, so we're told we want to make a 0.05 molar solution. We're told that. Now, what does 0.05 molar mean? It means moles per liter. So what we want to do is go from a number of moles per liter, and we want to find out how many grams we need to make it up to 250. Now, we have mole per liter solution, but we don't have a full liter of solution. We're not making a full liter. So first of all, we want to go from moles per liter to find the number of moles. So what would we multiply here to turn moles per liter into moles? Okay, so that's the first stage. At this stage, you may be able to pause the video and do the next bit. I'm hoping that you can. I'm just going to bring you back over and show you the numbers again. There's the numbers you need to know in part 2. Okay, and hopefully we're figuring out that if we want to turn moles per liter into moles, we need to times it by liters. Cancel them out. Okay, so what we were told was we wanted a 0.05 moles per liter solution. We weren't using a full liter, we were using 250 centimeters cubed. That's what we were making our solution to. Now, how much of a liter is that? Hopefully you can do that calculation in your head, especially if you're higher level. Okay, so 250 cm cubed is equal to 0.25 liters. Okay, so 0.25 liters. All right, so once you know that, then we have 0.05 times by 0.25, and that gives us a number of moles, 0.0125. So that's how many moles we would have in our 250 centimeter cube solution, or our 0.25 liter solution. Now that wasn't our final answer though. We needed to find out how many grams that would be. Okay, so the next step is we've got moles, and we want to convert to grams. Okay, moles to grams. Now, some of you know how to do that here. This is moles of Na2CO3, by the way, that's the substance. So how do we go to grams of Na2CO3? Pause the video and go ahead and do that now. Okay, there's a number of ways you can do this. Some of you will know a formula, but again, using unit analysis, which my students should know about, we can set it up as a fraction like this. Okay, so we times it by a conversion factor. And remember, we want our answer to be in grams, so some amount of grams, which means that we need to cancel out these moles of Na2CO3. I'm going to put it on the bottom because something in the numerator can cancel with something in the denominator, like that. So we can cancel those, and that means we need grams of Na2CO3 on the top. The relationship between moles and grams here is that for every 1 mole of this substance, we have the mass in grams of that substance. And we were told earlier on in the calculation that a molar mass was 106 grams here. So now that we've got that done, let's go ahead and do that calculation. Okay, the answer that I'm getting is 1.325 grams. So this is the quantity of Na2CO3 that we would have to make up to prepare a 0.05 molar solution of 0.25 liters. So that there is correct. Well done. All right, let's go back to the question now. And now we're getting to the stage of your pretty standard titration calculation. All right, let's see what it says here. It says the sodium carbonate solution prepared by the student was then titrated with hydrochloric acid of unknown concentration. So it's making it very clear for you here which one is the known and which one is the unknown. So the HCl is the unknown. The acid was added from a burette to 25 centimeters cube portions of the sodium carbonate solution. So sodium carbonate, it was 25 centimeter cube portions that were used. Here's the equation, and it'll always be this balanced equation. And then we have some more questions to answer. D, okay? So D asked, how was the conical flask prepared for use in this titration? So this is a pretty standard question. What do we do for the conical flask before we begin the reaction? All right, pause the video and write down your answer now. Okay, so D. All right, so the standard idea here is that all pieces of equipment need to be rinsed before the titration. Some pieces of equipment are rinsed with deionized water and then the solution they are going to contain, and some pieces of equipment are just rinsed with deionized water. Think about why this one would be rinsed with just deionized water, or would it be rinsed with this deionized water followed by the solution it's going to contain? Which do you think it's going to be here? Pause the video and write down your answer. Okay, so I'm hoping that you said the conical flask needs to be rinsed with deionized water. We don't want to say that it's then rinse with the solution it's going to contain. Why is that the case? Well, if you're not sure about this, remember what we're trying to do. We're trying to put an exact number of moles in here. 25 centimeters cubed contains an exact number of moles. It has to be very accurate. If we have rinsed this with the solution it's going to contain, and then we add the 25 centimeters cubed, there's a good chance that there's going to be some drops of this substance left in the flask, and therefore this won't be exactly 25 centimeter cubed anymore. It's going to be too many moles. Okay, so that's not going to help us. So this one's only rinsed with deionized water. Well done if you got that right. That was worth 6 marks. Give yourself a tick and give yourself 6 marks. All right, next bit is indicator. Okay, so E, indicator. So what you have to do is name the indicator suitable for use in this titration and state the color change observed at the end point. A nice 9 marker for you. E. Okay, so pause the video and writing down. I'll show you the equation again. It's up here. What indicator do we use and what is the color change? All right, so hopefully you were able to write that down. If you weren't, I'm going to give you some help. This here is hydrochloric acid. It's a strong acid. This here is sodium carbonate. It's not sodium hydroxide, which is our main strong acid. This is a weak base. So strong acid, weak base, what's the indicator? And then what's the color change? Pause the video, write it down. All right, so I'm hoping that you know this here, sob-mol. Most of my students know this because I tell it to them. What does it stand for? Strong acid, weak base, methyl orange. Okay, so the indicator here is methyl orange. You get 3 marks for that. And what is the color change? So if you couldn't remember which indicator it was, now that it's methyl orange, what would the color change be? Okay, well, methyl orange is is yellow in a base and red in an acid. Okay, so the first question is, what is it mixed with in the conical flask originally? So what is in the conical flask? Okay, here you can see the sodium carbonate is in the conical flask. That's the base. Remember, methyl orange is yellow in a base, red in an acid. Okay, so that means we should get yellow in the beginning because it's mixed with the base, and it turns to red at the end when the solution turns acidic. So yellow to red is the color change at the end point. All right, so that there is what 9 marks. You're going to get 3 for this, 3 for this, and 3 for this. Well done if you got all 9 marks there. You're seeing that these aren't that easy, right? This question is, if you're used to the higher level questions, this question is not that much easier, but it is a little bit. They give you more information. The information's clearer. All right, let's move on here to the end here. It says the average volume of HCl required to neutralize a 25 centimeter cubed of the 0.05 molar solution of sodium carbonate solution was 20.1 centimeters cubed. Calculate the concentration in moles per liter of the HCl solution used. So all we have to do is calculate the moles per liter of the unknown. So there's no extra step in this one like there normally is in the higher level. The process is still the same. I always advise my students to write out the balanced equation. So pause the video and write out the balanced equation now, please. All right, so we've got 2HCl plus Na2CO3. And then the rest isn't really important because what we're interested in is how do these interact with each other. The first thing to do is to identify which one's the acid, which one's the base. First of all, this one's the acid and this one's the base. And now write down the reactant ratio. Pause the video, write down reactant ratio up here. Okay, so 2 moles of acid react with 1 mole of base. That's going to be important. All right, let's go ahead and figure out then a plan for how we're going to do this. You may be able to go ahead and do this without any of my help. Hopefully you are. So what I'm going to do is I'm going to ask you to pause the video, and if you're able to, have a go at working out this concentration now of the HCl. Pause the video and do that now, please. All right, if you're not able to do this by yourself and this is one of your first times doing this, then the first place to begin here, I always get my students, I ask them to draw 2 arrows from the acid and 2 arrows from the base here at this point, like this. Now these 2 arrows, one of them is for concentration, so moles per liter, and one of them is for the volume used in each titration, in liters. Now you'll notice that they always give you the volumes in centimeters cubed, but it's easy at this stage just to convert to liters now. Okay, so how do we convert to liters if we've got cm cubed? Good question. Okay, so say we have a number of cm cubed, 100 cm cubed. What I would get my students to do is times it by a conversion factor, which is a fraction. And what we want to do is we want to convert between the two units. We want our answer in liters, and we want to get rid of centimeters cubed. Centimeters cubed here is in a numerator, so it's on the top of there's no fraction, but it's on top. So this is what we call a numerator. So if we put it in the denominator of a fraction and multiply, we can cancel out centimeters cubed, and we can leave liters on the top. Okay. The next question is, how many centimeters cubed are there for a liter? Well, for every 1 liter, there are 1,000 centimeters cubed. So now we have a sum to do, which can convert centimeters cubed to liters. You'll see that your only unit left is liters. So that has to be the unit in your answer, which is what we wanted to get. And that's how you'll always know you're right, because you'll be left with the units you were looking for. All right, so go ahead, pause the video and do this now. Okay, what you're going to get is 0.1 liter. Okay, so that's if you had 100 centimeters cubed. Another way you can think of this is if you have 100 centimeters cubed, that's 100.0, remember, because it's 100. To convert to liters, you just move the decimal place 1, 2, 3 places to the left point there, and that means that this is, you move it. Yeah, here's 100, you move it 1, 2, 3 places to the left, so this becomes 0.1 liters. Okay, all right, so let's apply that here. Here it says the average volume of HCl, so this here, required to neutralize a 25 centimeter cube portion of the 0.05 molar sodium carbonate solution was 20.1 centimeters cubed. So the first thing to note is which volume goes with which. The HCl, the volume used was this. I know that may be hard to spot, but read it carefully again and it should make sense. You have to read these phrases very carefully. And that means that the 25 centimeters cubed and the 0.5 molar belong to the sodium carbonate. All right, so what we're going to do is we're going to plug them in down here. All right, sodium carbonate we know is 0.05 molar. So I'm going to write that here, 0.05 molar. Okay, and what volume did we use? Well, it was 25 centimeters cubed of the sodium carbonate, and I want that in liters. Okay, so if you're not sure how to do it by moving the decimal place, then do it like this and write it down here in liters. Pause the video and do that now. Okay, hopefully, if you've got 25 cm cubed, 25.0, you can also go, okay, we've got to move it 1, 2, 3 places to the left, which is going to give me 0.025 liters. Okay, so 0.025 liters. What we're doing with the acid then is we are looking at this concentration, this volume here, and we're converting that to liters because that's for the acid. Pause the video and do that now. Okay, what we should have got here is 0.0201. And our concentration of the acid, well, that's our unknown. That's what we're trying to find, because look what it says. Calculate the concentration in moles per liter of the HCl. So this here is a question mark number of question mark molarity. All right, at this stage, we need to come up with a little plan. We've got to start with the thing we know and work towards the thing that we're not sure of, or the thing that we're trying to find. So again, some of us at this stage may know how to do this by ourselves. Okay, this is part F. If you do, you can pause the video and go ahead and see, can you work this out? Pause the video, do that now. Okay, so I'm just going to, first clue I'm going to do is I am going to give you the answer, okay? So I am going to give you the answer. Your answer that you're looking for here is 0.124 moles per liter. Okay, so 0.124 moles per liter of hydrochloric acid. If you got that, well done. If not, then let's watch along and see what happened, what went wrong. Okay, we need to come up with a little plan for how to do this. The first thing we got to do is we work with the thing we know. Okay, and what we're going to do is come up with a plan. We know we have moles per liter of Na2CO3, moles over liters. We know that, that's that one there. And what we're going to do is find out how many moles we use per titration, because we didn't use a full liter. So we're going to times it by a conversion factor in liters, and that's going to give us a number of moles. Okay, because liters cancels with liters and leaves us with moles. Okay. All right, so we're going to pause the video and let you do that bit. Okay, so what we're going to do is, how many moles per liter do we have? Well, here it is, 0.05. So I'm going to fill this in, 0.05 moles per liter. We didn't have a full liter, we had 0.025 liters. 0.025 liters, which means we get your calculator out and do this. It means we had 1.25 by 10 to the minus 3 moles of Na2CO3. All right, the next thing that we are going to do is we are going to convert and find out, okay, if we had this many moles of sodium carbonate, how many moles of hydrochloric acid did we have? Okay, per titration. So the next step is to go from moles of Na2CO3 to moles of HCl. Okay, so you're going to pause the video and convert that there now. Okay, so quick reminder, you're going to need to use the reactant ratios here. Okay, so set up conversion factor again. And we need moles of Na2CO3 to cancel because we don't want that anymore. We want moles of HCl. So I'm going to put it in the denominator here, moles of Na2CO3. And I want to be left with, so they cancel, and I want to be left with moles of HCl. The next thing I do is I go to my reactant ratio up here, and I see it's 1 Na2CO3 to 2 HCl. So 1 to 2. So that means I need to double my number of moles. So times by 2. And that gives me 2.5 by 10 to the minus 3. 2.5 times 10 to the minus 3. And what's the units? Well, it's this here. It's the only unit I'm left with. It was moles of HCl. Okay, so now that I have moles of HCl got per titration, I want to know how many moles per liter is that. Okay, so I'm going to go to moles of HCl per liter. Okay, now that means that I need to turn this unit here into moles over liters, moles per liter. And I need to find out, well, how many liters did I use in a titration? And as you can see here, we worked it out up here that it was 0.0201. 0.0201 liters. Checking my units to make sure they're right. Here we go, moles over liters. Okay, so I know I've got it right. It's moles per liter of hydrochloric acid. So now I just need to do this sum now to find out my molar concentration. And there it is. And I do my sum there. It's 0 equals 0.124. And that my units here are moles HCl in 1 liter. Okay, so that there is my final answer here. All right, so that was the first video in our Back to Basics series. You know that in a higher level calculation, there would typically be more steps than this, but that there would be very similar to the first step, and it would be probably worth 6 or 9 marks on a higher level. But it's good to go back to some of the ordinary levels and just work our confidence up, build our way back up, build our way up to being able to answer the harder problems. Now, on the future videos, I'm going to move a bit quicker. I'm going to not explain the workings, the conversions so much. I'm going to assume you guys know how to do those now after seeing this one. So you should be aiming to be able to get one of these done in 10 to 15 minutes. Okay, to get a full question on an ordinary level done if you're a higher level student. All right, so I hope that you found this useful. And I look forward to seeing it in the next one. If you've got any questions, please stick them in the comments below and I'll chat about them in the next video.